Welcome everyone to part one of template normal programming. This is template metaprogramming without the meta part. I will be your guide on the next 2 hours and 15 minutes. And I say that because we might go into the break, who knows. But yeah, so what are we actually talking about here? What should you expect to get out of this particular talk? Well, so I looked up the definition of metaprogramming, and I looked up the definition of programming, respectively. And Wikipedia says programming is the craft of writing useful, maintainable, extensible source code which can be interpreted or compiled by a computing system to perform a meaningful task. I looked up metaprogramming. That, according to the designer of someone in the audience knows which language this guy designed, I forget, the writing of computer programs that manipulate other programs or themselves as if they were data. And I got the impression going to a lot of talks at conferences like this that were about templates in general. They ended up being about template metaprogramming, which is to say programs that spend a lot of time manipulating themselves and not a lot of time performing meaningful tasks. So I thought I would try to give the beginner's overview of what are templates, how do we use them, how can we use them effectively, and do it without mentioning SFINAE, and do it without mentioning type traits, but still give you some interesting stuff. I hope this will be interesting. This is stuff that was interesting to me writing it, so I hope it'll be interesting to you hearing it. So motivation. What are templates? Why are they in C++ to begin with? Presumably everyone has seen a slide something like this before. In C++, well, in C, we have a function like abs, and it takes an int and returns an int. And in C99, well, you know, later on they realized that they also need a version of this for long, and they need one for long. And by the time you get to C99, you have about a dozen absolute value functions in the language, and they all have different names. This is fun, but we can spend more time doing meaningful tasks and less time manipulating our programs if we allow function overloading. So C++ from the very beginning allowed function overloading. You can have functions that take different types and return different values and maybe even do different things. We would like to, even writing this is too much code for us, right? We'd like to collapse it into some sort of template. A function template is not a function. It is a template. It is a template for making a function. It looks something like this, and it gives us a recipe for stamping out copies of the abs function with different t's, right? You can get abs of int from this, you can get abs from double from this, and so on. And we don't pay for what we don't use, right? With the overloaded version, we have two functions. We compile, we code gen two functions. We pay for two functions all the time. In this version, we can, through the magic of implicit instantiation, which you'll see in a minute, and by a minute I mean 2 hours, you know, you won't instantiate the code at all. Using a function template looks something like this, again. Down here where we make the call to it, we have to tell it how to instantiate this template. What is the type T that we're instantiating it for? And this is the simplest possible way to do that. You just say the function name, or the template name, the name of the function template, abs, and you give it the template argument T in angle brackets. Makes sense, right? It will not be instantiated with any particular type foo until you, the programmer, explicitly mention that you would like it instantiated for absolute value of foo. As soon as you mention that, the compiler has to go instantiate it in order to figure out, you know, what is its return type, what are its argument types, and so on. Now, sometimes the compiler can deduce that you mean absolute value of foo. For example, in this case, it can actually deduce both of those. But we'll talk about deduction later. Hold that thought until slide 21, it says, but then I rearranged all the slides, so I don't know when that slide is coming. We have the same concept for generic types, right? Generic functions, generic types. We've also seen this sort of thing. If you've done any C, you know, you manipulate a lot of void stars, and you have no type safety, type punning, error prone, ugly. Or you could have something like this, where maybe you generate this using some macros of some sort. We have mylist of int and mylist of double. Obviously, we'd like to have a mylist of t, and you probably do have a mylist of t macro if you're programming in C. And in C++, we formalize that by making class templates. Again, a class template is not a class. It is a template for making a class, making many classes that follow the same basic outline of stuff. And don't pay for what you don't use. If nobody uses my list event, it won't be instantiated by the compiler at all. Template classes are still classes. Wait, well, I just said the opposite, didn't I? We have some terms of art here. Sometimes when people say template class, they mean class template, which is not a class, it's a template. However, some people, like I think Scott Myers and possibly even the standard, when you reverse the words, a template class is a class generated from a template. A template function is a function generated from a template. So if I have a class template and I use it to generate a particular class, such as in this case, well, in this case I don't have a template yet, but I will if it were like s of int. That itself is still a class, and it follows all the general rules for making classes, such as your static data members have to be defined somewhere if you want to use them. So here I have a class that is not a template class. It's just a regular class, struct s, and it has a static data member, and I try to use it in main, and it tells me, well, I get an undefined reference in the linker, right? How many people have seen a linker error that looks like that from trying to use static data members? All right, yeah. And then you do this, and it works, and that's awesome. And then you do this, and it breaks again. How many people have seen this? Yeah. Templates suck, right? But they followed all the same rules of the regular classes, right? Just like in this case, where I didn't define SDM. Well, if I add a definition, now of course my definition needs to be templated, right? Because you know, I don't know which ST I'm going to use yet. But if I make a template for stamping out that definition, then it ends up working just fine. Now the interesting thing about this particular example, is that I can actually put that definition of that static data member in the header file for a template. I can't put that in the header file for the regular old S where it wasn't a template. But when it's a template, I can just sort of shove everything in a header file and it basically works. That's actually kind of interesting because you can't do that with normal things. But you can do it with inline things, right? Inline functions, and as of C++17, we have inline variables, which Bjarne talked about this morning. He hates them, but I love them because why can't you just put inline on everything? It makes sense. Just throw it all in a header file, and it all works. Well, so the same rules. Basically, if you think about how inline functions work, the same rules govern how templates work, basically, more or less. If you can make something work with inline, you can probably make the exact same thing work with template. And we'll see that more later when we get into instantiation rules, which was the slide formerly known as slide 21, I think. Right, cool. Oh, I forgot to mention entirely. Let's go all the way back to the beginning, by the way. I have 3 links at the bottom here. The first link is a link to the current draft standard, which is freely available. The draft standard for the C++ programming language, it's N4606. And whenever in the lower right-hand corner of these slides, you see a little thing in purple that has like a section number and all that, you can actually go look up in the standard, for those of you in the audience who like looking at the standard. Don't go to Netflix, but you know, do read the standard, I guess. It's not multi-gigabyte yet. And the 2 other links here, Wandbox is a free way of compiling code online. As long as it fits in a single translation unit, you can use GCC or Clang and find out what their output is for a particular thing. You can test if that code works in current, like top-of-tree Clang and GCC. And webcompiler.cloudapp.net is a Microsoft thing, does the same thing for some version of MSVC. I'm not sure which, but if you want to test things on MSVC, that's another way you can do that. As long as the internet works, which apparently doesn't quite at the moment. All right. So down here, when you see the little reference to N4606 section, that's what that's referring to. And it's where you can go for more information if you wanted about the wording that governs inline functions and also templates. So there are 2 relatively new kinds of templates. The kinds I covered already, function templates and class templates, those have existed basically forever. They were to C++ 98. In C++ 11, we got alias templates. And in C++ 14, we got variable templates. I'm going to talk about variable templates first because they're a lot like class templates. In fact, they're basically syntactic sugar. They're basically syntactic sugar for static data members of class templates. So here we have an example of a class template with a static data member named value, and it's static, and it happens to be const or bool, you know, and those bits don't matter, but it's static. And we can print out its value and so on, and forget the sum expression for now. Here's the variable template version of this. It's very similar, except we took out all the class bits because it turned out we didn't really want them. They were just sort of extraneous. We needed them in C++ 98 to get this functionality, but now we have variable templates, and they just look like this, right? It's still a template, and then it looks like a variable declaration. Notice the word static is gone because it's no longer a static data member. Now it's just a regular old data variable, a global variable. And we can initialize it the same way, and we can stick this in a header, and it will magically work by the same rules that make inline inline variables now work. For things in the STL, by the way, we get the best of both worlds in that stuff that's been around for a long time will tend to be implemented as these structs like isVoid. This is a type trait, which I'm not going to talk about much, but you have isVoid here with a static context for bool data member, and then we have another. Outside of the class, we have this free-floating global variable called isVoid _v that's just defined as the value of the class. So when you see all these _v's and _t's, they tend to be aliases for things that already exist. And this is a nice pattern to follow in your own code if you're writing things like type traits, which I'm not going to cover much because I'm not going to talk about metaprogramming. Is that a question? Previous slide. Why would I write something like this given that the fact is the template is not really being used? Well, it depends on what some expression is. Some expression could be something that depends on t. In fact, in this case, it should be something that depends on t, because if t is void, we want it to come out to true, and if t isn't void, we want it to come out to false. But that's metaprogramming. I'll show that later. Any other questions, by the way? We've gone through a bunch of slides already. Cool. All right. So let's talk about alias templates. This is a different kind of beast for reasons that we'll see. But you can think about the basic idea the same way. In C++ 03, and of course in C, we have type defs. And right around C++ 11, they decided that the name for these things was not really type defs, they were really aliases. Let's call them aliases. But it means the same thing. It's one type being an alias, a synonym for another type. And so you can take, as in this example, I have the old type def syntax to make myvec int. I then make a very similar thing called myvec double using the C++ 11 alias syntax. It doesn't actually use the word alias, it uses the word using. So maybe they should have called them usings. And then also in C++ 11, we got the ability to take this new syntax, not the old type def syntax. Forget the old type def syntax ever existed. But we can take the new syntax for making aliases, and we can make templates for stamping out aliases. Right? This is an alias template. And so by itself, it does nothing. But when I instantiate it, as with the last line here, and I say myvec of float, it'll go and it'll say, OK, well, how do I make a myvec of float? Ah, I see. I would use the alias template and instantiate it for float, and it becomes, oh, it's a std vector of float. I get it. And in fact, those become the exact same type, right? They are literally, kind of already made this point, but just to hammer this in, they are literally the same type. So if I have this function f that takes a myint, which happens to be an alias for int, I can pass an int to it. Right? I have an int, I pass it to a function expecting myint, and it just works because they're the same type. Likewise, I can have a std vector of int, and I can pass it to a function expecting a reference to myvec of int. And it will just work because they're exactly the same type. You know, one is not derived from the other. It doesn't have a member type, the member type def that comes out something. They're literally just exactly the same type as if you had used a regular alias to make them synonyms. All right, so now we've actually covered, we hit a milestone here. This is meaningful. We now know all the different kinds of templates in C++ 11, or in C++ 14, rather. And they're exactly the same as they are in C++ 17. We didn't get any new kinds in 17. So now you're completely up to date with C++ 17. So let's talk about type deduction. Hey, look at that. It's still slide 21. Awesome. So type deduction. right? So we're back at this state where we're trying to use abs, which is a function template, and we're trying to instantiate it for a particular type t, and we just want to use it without all of this extra angle bracket syntax. So here's how it works. Did I skip anything? No. This is how you might experiment and find out for yourself what type t is deduced for various kinds of call expressions. I should explain at the very top here where it says put s of pretty function. How many people in the room have seen pretty function? How many people in the room haven't seen pretty function? Nice. It's like 40-60, yeah, 50-50. So what is pretty? So pretty function. How many people have seen under function? Under. Okay, so all of these are magic macros, basically. They're expanded sort of by the preprocessor, sort of. And for example, under function expands the name of the function. So if I'm in a function called main, then under function expands to the string main. And I can use that just like it were a string literal. It's just like under file, under line, right? They just expand to these constants that I can use as if they were macros substituted in. So function expands to the name of the function. Pretty function in GCC and Clang expands to a pretty printed name of the function that just happens to include is it a template, and what are its template parameters, and what were they deduced as, right? So when I put as pretty function, I actually get something out. You see those comments there? That is literally what this code prints. I run this code, and it will actually print a void foo paren t bracket t equals int close bracket, new line. So this is super useful. If you're ever trying to get into the nitty-gritty of type deduction, or which of my templates is getting called, or why is t deducing as something I didn't expect it to, using pretty function is definitely the way to do that. MSVC has something, the closest thing they have to it is something called funcsig, with double underscores on both sides again. It's not quite as pretty function, but then it doesn't claim to be. Okay, so in this case, we're just passing in a bunch of these values, and as we expect, foo of 4 comes out to call foo of int, and foo of 4.2 calls foo of double. Foo of hello calls foo of const char star, which is actually a little bit weird if you recall that string literals actually have array of char type. But that's just because we're taking it by value, and so it happens to decay to a pointer, and there's rules for that. But mostly I'm going to ignore the whole array case, because that's a little scary. But let's talk about type deduction. Let's go deep. Here's the deal with type deduction. This was a particularly trivial case because we had one template parameter named t and one single function parameter called x that just happened to have type t. So this is the most trivial case you can get. But in general, when I have multiple template parameters or multiple function parameters, here's what happens. First of all, each function parameter by itself, each function parameter, can contribute to the deduction of each of the template parameters. Or it might not. It might not have anything to say about that template parameter. In our case, x is of type t, so it definitely contributes to the deduction of type t. And then if I had a second parameter, y, it would contribute to the deduction of whatever template parameters it was of. All of these deductions, the deductions for x and deductions for y, deductions for z, etc., are carried out in parallel. They don't really crosstalk with each other. So we deduce what does x tell us, what does y tell us, what does z tell us, and then we compare notes. And we say, oh, well, x told us that t was int, y told us that u was double. Okay, so I guess t is int and u is double. And we need to make sure that we deduce all the template parameters we can, and that all the deductions agree with each other. If x is saying that t is int and y is saying that t is double, well, they can't both be right. There's a disagreement there, and we got a compiler error. So there's deduced conflicting types for parameter t. And then there's one last rule, which is going to trip us up later, which is that any function parameter that does contribute to deduction has to match the function argument type, the argument being the thing you actually called it with, has to match the type of that argument exactly, with no implicit conversions, no integer promotions, nothing like that. And that the reason is basically to keep things from getting out of hand. If you also allowed implicit conversions there, that would just be an extra level of maybe accidentally calling the wrong template. So at the very end, we lock that down and say the argument types need to match exactly. So let's look at an example. Let's look at 3 examples. Here we have a function f. This is the second most trivial case. It has 2 template parameters and 2 function parameters, x and y, that each contribute to exactly one of the template parameters. And if I call f of 1, 2, well, 1 is an int, so x is an int, so t must be int. And completely separately from that, y is 2 is an int, y is of type u, therefore u must be int. And so we deduce that t is int and u is int, and we compare notes and find out there are no conflicts, and we have deduced t and u, and we're all set. Okay. Now with g, g has 2 function parameters, but only 1 template parameter, t. Fortunately, x says, well, t is int. Y says t is int. They compare notes. They agree. Yes, t is int. We are in agreement, and it works. Now in the second g case, x says t is int, right, type of 1. Y says, well, I got an unsigned value. T is unsigned int. And they do this separately, right? And then they compare notes, and they say t is int and unsigned int. Nope, that's not a thing. We disagree. And so you get an error. No matching function for call to g of int, unsigned int. And the wording of the error message may vary a little bit, and it doesn't really matter. The important thing is that that's why it happened. The function parameters deduced that t was different things, and that's the end as far as template type deduction is concerned. You might say, well, why doesn't it just like promote them both to unsigned int or something like that? Normally happens, but nope, doesn't happen in this case. Very simple rules for template type deduction. And we should be thankful for that, because if they were complicated, who would ever understand them? Certainly not this entire room in 2 hours. Can you believe that? Question, yes?
One of the problems with not allowing implicit conversion is that if you call standard min with 2 and 3.2, that would not work.
That is correct. How many people have seen this?
Oh yeah, that's fine.
And using stdmax? Yeah, so here we have a function f that happens to return a short, or it could return unsigned int, or whatever. And we just want to max that with 42, right? I mean, I didn't even need to make up int x in this case. I could have just said stdmax of f, 0, right? And again, I get error, no matching function for blah, blah, blah. And the reason is the same thing. Stdmax only has 1 template parameter, right? T. And it takes 2 arguments of type t, tx and ty. And in this case, the first x says t is short, and the other one says t is int, and they disagree, and you get a hard compiler error. This is one of the downsides of this rule. There's a slide that follows that, but first, let's do these puzzles in order. Which of these 2 calls to foo ought to compile, and which not? I'll let everyone sort of digest this for a little while. But then I'm going to answer it anyway, because the answer is half on the screen. So the first one takes the 2 function, or the 3 function parameters. There's x, y, and z, okay? And we're calling it with a std array of int 8, a std array of double 4, and 0.0. 0.0 is actually part of the puzzle here, right? Because that's a double, and z is an int. But z doesn't depend on any of the template parameters, t and u. It does not contribute to deduction in any way, right? Because there's nothing we could possibly put in for z that would tell us anything about t or u. It's always supposed to be an int. So z does not participate in type deduction. X, on the other hand, does. What can x tell us about t and u? Well, it can tell us exactly what t is, right? Because if I pass the std array of, in this case, int, something, well, t has to be int. There's no way it can be anything but int. So x contributes to the deduction of t. Does it contribute to the deduction of u? It tells us the size of u. Does that count? Turns out not really. because that's not something that the compiler can really figure out. I mean, even if it did try to figure it out and said, okay, well, I see that size of u must be 8. Like, how's it going to record that? Where in its table of information about u is it going to say, well, I don't know what it is, but I know its size. Maybe that'll help. But that won't help. So it just forgets that. X does not contribute to deduction about u because it doesn't tell us anything directly relevant. Right? T, it tells us exactly what t has to be. U, it doesn't tell us anything but the size, so we don't care. So from the first parameter, in the first example with state array int 8, x tells us that t is int. Y, for the exact same reason, tells us that u is double. And z doesn't matter. We compare notes. None of our notes disagree, and we know what t is, it's int, and we know what u is, it's double. So now we do that last step, and we check, and we say, okay, well, so that means x has to be of type std array of int, comma, size of double is 8, I'm getting a std array of int 8, yep, that all checks out. And it does the same thing for y, and yeah, that all checks out. And then z gets an int, but it didn't participate in type deduction. So it got a double, that's fine, we'll just convert it to int, that's fine. And so the first line compiles. The second line, we go through all the same type deduction, we figure out that t is int and u is double, and then we look at that first argument x, which did contribute to the deduction. And it's a std array of int, comma 9. That's not int, comma 8. That's a different type. They needed to match exactly. Doesn't even matter if there is an implicit conversion there. They needed to match exactly, and they don't, so that's a hard error. Is everyone following that? All right. Here's a similar thing, and this is, again, inspired by real stories. Let's say I have a function foo, and it takes a function pointer of some sort, and the function pointer takes one argument of type A and returns something of type R, and luckily I can deduce those when I pass in a function pointer. Right? I can say, well, if this is double star f pointer parens int, well, then I guess R must be double and A must be int, and so deduction will work for R and A. The problem is if I pass it a lambda. Right? A lambda, a captureless lambda, is always implicitly convertible to a function pointer type. By the way, if you didn't know that, now you know that. Lambdas are awesome. But being implicitly convertible to a function pointer type doesn't help you call foo with it. Because again, the type needs to match exactly, and the captureless lambda type itself, while being implicitly convertible to a function pointer type, is not itself a function pointer type. And so you'll run afoul of that very last step. Pro tip here is if you absolutely need a function pointer out of a lambda, just stick a unary plus on the front. There is no unary plus for lambda types, but there is a unary plus for pointer types, function pointer types. And so it will do the implicit conversion before it applies unary plus, and the thing you get out of the unary plus is in fact the function pointer itself. Unless you're on MSVC, and then you get a confusing error message. Because they have 4 different calling conventions, and they don't know which one you mean. All right, so now we get back to the slide with the stdmax. How many people have seen this? Everyone's hand should be up. We just did this. All right. All right, so there are 2 ways to solve this problem, right? The problem being that this stdmax call does not compile. One of the ways to solve it is so every parameter that contributes to deduction must match its argument type exactly. So our 2 ways of solving it are either to make the argument types match exactly, or make the parameter stop contributing to deduction. So the first way, make the arguments match exactly, looks like approach number 1 there, where you're just taking a static cast it to int, right? How many people have done something like approach number 1 at some point in their code? All right. I advise doing approach number 2 instead, just because I feel it's more readable. So return stdmax angle brackets int, and approach number 2, the thing we're trying to do there is make the parameter stop contributing to deduction. All right, so let's go back to type deduction in a nutshell. Well, how to call specialization explicitly. Basically, I'm just putting the type of t right there in angle brackets. How do I do that? Oh, I thought I was going to have another slide about type deduction in a nutshell here. Well, the stuff in angle brackets, after I name the template and I tell you which template I'm using, in this case add, I can start giving you the template parameters explicitly. I can say, going through the template parameter argument list, starting with t in this example, I can say t is int, and u is int. And now I have given you exactly the template parameters. Template parameters go in the angle brackets. Function parameters go in the brown brackets. I've given you exactly what t and u are. And that means that x and y no longer really have anything to say here. X would have told us about t, but we already know what t is. We told you it's int. Y would have told us what u is, but we already told you it's int. Therefore, x and y no longer participate in type deduction. Therefore, they don't need to match exactly anymore. And I will actually call add of int comma int with char value x. Normally that would be a char and it wouldn't work, but now that I've told you, just make it an int. It no longer participates in type deduction, and so the implicit conversion kicks in and it converts it right to int. And similarly, the 3.1 is a double, but it gets converted to int because I told you that's an int. It doesn't participate in type deduction anymore. Now, all of these template parameters, t and u and so on, I can specify them, but I don't have to. I can specify only a prefix of the whole list. So I can say add of just int, and that tells you, well, t is int, but I didn't say anything about u. So now x no longer participates in deduction, but y does, and it tells us what u is. In this case, it says u is double, and we say, OK. I can even put nothing in the angle brackets, and that means I'm not telling you about t or u. Or in the case of function templates, I can actually omit the angle brackets altogether. And that's what you see most commonly in practice. So type deduction in a nutshell, any template parameters that were explicitly specified by the caller are fixed. They don't participate any further in deduction. And then all the stuff we saw before. Let's talk about this little red underlined bit. Remember, when we compare notes, we need to make sure that each template parameter has been deduced at least once. So if we have a case like this, here this takes no arguments at all. So t cannot be deduced. Fortunately, I can tell it explicitly that t is int in the angle brackets, and then it's perfectly happy and it works because it knows what t is. If I don't put anything in the angle brackets, or if I remove the angle brackets altogether, which is what you usually see in practice, then it doesn't know what t is, it can't deduce it. It says couldn't infer template argument t, and that's a hard error again. What do we do about this? Well, we can default the template parameter. Question? Is there a way to specify only the second template argument u? No, there is not.
Is it written in standard that the deduction will happen from left to right?
Is it written in the standard the deduction will happen from left to right in the order I described? Yes. And left to right order is also kind of magic when you think about can I write function parameters that have default values, right? Like once you start writing the default values, you have to keep going. You can't say there's a default for the second parameter and not the third. So we like left to right. It's a left to right language. OK, so in these cases, we can't infer it. We add the equals char star. Suddenly we can infer it. So even if it's not provided, it works fine. So let's add that to our template deduction in a nutshell here. If any template parameter that wasn't specified by the caller couldn't be deduced, but it has a default value, that's still OK. We'll fix it as its default value. And then we compare notes, and then we look to make sure that things match the function argument types. Cool. Now you actually know everything there is to know about template type deduction. Like, wow, that's all the rules. That's cool. Oh, yeah, OK, fine. No, if there's no ampersands, we're OK. All right, so let's talk about ampersands. Remember this? This is the trivial case. We have just a plain old t. We pass it an int. It comes out as int. No surprises. Let's talk about this. Now we have a t star. Now I kind of alluded to this earlier when I did the std array example, and you saw how I can pull a t right out of the middle of an expression and deduce that. Right? Out of the std array of int, I can deduce what t is because I said std array of t, that matches std array of int. T must be int. In the same way, if I'm expecting a t star and I get an int star, I can deduce that t must be int. All right. Now I'm going to assume some knowledge here of L values and R values. Because it's been 5 years, people. So here, this is an L value reference, single ampersand. And I'm taking an L value reference to a t. And the thing I'm passing to it is a named variable named I, which happens to be of type int. And that means that the expression I is an L value. Does that make sense to people mostly? In brief, L values are objects that would be missed by someone. such as I, because it's got a name and probably family and friends who would miss it. R values are expendable objects. They're survived by nobody. Nobody will mourn them. And so it's okay to stomp on the R values. But here, I is not an R value. There's no R values in this at all. We have I is an L value. We're expecting an L value. And so we can deduce that, okay, I'm expecting this reference to a thing, and I'm getting a reference to a thing that's an int, so okay, it's an int. Just like the pointer example, kind of. Makes sense, right? All right, let's do R value reference. Here, I have an f is expecting t ref. That is to say, an R value reference to a t. And some of you are preparing to raise your hands, but don't. An R value reference to a t, and so I pass it an R value, like 42. That's an R value of type int, and so t is int. Works fine. I pass it std move of I, std move being the magic thing that turns things into R values. And it works fine. Okay? Deduces int. Now let's try passing it just I without the std move. We pass an L value reference to an int. What happens? It still works, but it deduces that t must be int ref. An L value reference. This is interesting. Something interesting is going on here. What's going on here is something called reference collapsing. Scott Myers calls this he calls it a universal reference, but forwarding reference. But you can also just think of it as an R value reference to a t, and as long as you know about reference collapsing, you'll be all right. The rule to remember when dealing with references is that when you combine two reference types, when I take a reference to a reference, it basically mins the number of ampersands between them. So if they both have one ampersand, they're both L value references. An L value reference to an L value reference is an L value reference. An L value reference to an R value reference is an L value reference. An R value reference to an L value reference is still an L value reference, because if anyone would miss it at all, then someone will miss it, right? If anyone's got an L value reference to the thing, it's an L value reference. But if everything involved is R value references, then it's okay. We've still got an R value reference. So what's going on here? Well, we have f of I. I is an L value int, which is kind of like an int ref. Let's say it's an int ref. So we need to deduce t up there. We have t ref. We need to deduce t such that t, R value reference to t, is L value reference to int. So obviously t can't be just plain old int, because then t ref would be int ref, which is not int ref. It can't be int ref either. That wouldn't work. But if we make it int single reference, an L value reference, then an int ref is still an int ref. We give it an int ref and it all works. And it works. Does that make sense? Ref. All right. So if we give it an R value reference, here we have an R value reference to an int. We're passing it to a function that expects an R value reference to a t. I think we already saw this. Of course, it deduces t equals int. Now you might say, why doesn't it deduce int ref? Because that just as well would work. And the answer is that's too many letters, too many characters. Like, why bother sticking the ampersands on there if you don't need them? So it will prefer to deduce int. Does this mean that int ref is never deduced? No. Like here's a case where like obviously t has to be int ref or it wouldn't work. But basically, if you've got any ampersands at all involved, then yeah, you're never going to see it deduce an R value reference. Questions about this one? What's that?
Temporary is the word. If you pass in a temporary return value, you would see it deduced.
If I pass in a temporary to the function that it just expected a t?
Yeah, a t ref.
Expected a t ref. No, that's exactly this case, isn't it? Where I'm passing in basically a temporary. I mean, it could be 2 plus 2 just as well. And the thing that t deduces as is just int. The function parameter type is int ref, but all right. So reference collapsing, this is a very important thing to know when you're dealing with templates in C++11 and later. It is less important, but it was still present even back in C++03 with L value references. Suppose I have a function, f, that takes R of some type, and then it tries to construct an R ref. And I instantiate it with R equal to int ref, as I'm doing down here. Do I have a pointer? Right there, right? So a ref to a ref collapses to a ref. This was not standardized. This was an extension pretty much, but every compiler vendor had to deal with this if they were going to do templates. So everyone pretty much kind of knew that, yeah, this is how it should work. But it was not standardized until 11, and by 11 we had to deal with this exact same issue with R values. Is the question?
Yeah, so on your previous slide there where you had, and also on that one where you were talking about how you have a ref passed to a template that's a ref, an L value on the template, but an R value that you're passing in gets converted to an L value when it's in the template.
Yeah, let me find
if you
this
were
guy.
If you were to call another function, you'd be calling the L value, like if you're trying to call a constructor or something, you'd be calling the L value constructor on that rather than the R value once it's in the template.
Right. Once you're inside a template that takes an R value reference or an L value reference, are you then using that parameter when you use it to call some other function? Does that come out as an L value? And the answer is yes, always for any template parameter, because template parameters have to be named. Right? You have to name your template parameters. Well, you can leave it blank, but then you can't use it. So if you're using it, you must have a name, and if it has a name, someone would miss it if it disappeared. So anything with a name is always an L value regardless. Yeah. So even in this case where t deduces as int and the parameter lowercase t is of type int_ref, if I were to actually pass t to some other function in here, t has a name, I would care if it disappeared on me. So it would be an L value at that point. And I would have to std move it again if I wanted to turn it back into an R value. Okay, let's talk about more reference collapsing, but this time let's throw const volatile in there, CV qualifiers. So in this case, I have a const int. I'm passing an L value to a const int into a function, expecting a forwarding reference here. Let's do some reference collapsing. I is const int ref. We want to deduce t such that an R value reference to t is still a constant ref. Well, const int by itself does not work, but I add a single ampersand to that, and it does. So that's what the answer is. T is const int ref. Do the same thing with std move of I there. That's a const int R value reference. We should deduce t such that t ref is const int R value reference, and const int works fine. So that's what we have. We have f of const int is the answer for that one. Okay, now let's stop talking about these forwarding references because they're too easy. Everything just works with them, right? Let's go back to L value references. So I have f of tref here, and I try, in this case I'm just using the static casts to just explicitly specify what are the types of these things that I'm trying to show. So if I pass in an int ref, obviously I get int because tref is int ref. If I pass in int ref, there is nothing I could possibly do to make t L value reference come out as int R value reference, right? Because I'm minning the thing. So this might be confusing until you realize you're probably thinking about it backwards. So int ref turning into an L value reference, there's nothing I can possibly deduce t as to make that work, so that's an error. And if I stick some qualifiers on there like volatile int, well, things deduce pretty much as you would expect. Right? And then I go to const. And the interesting thing about const is it all works exactly as you would expect, except that last line where I cast it to a const int R value reference. And somehow that works. That will call f with t equal to const int, and it'll take a const int ref parameter. That's interesting. That's an R value reference quietly working with a function that takes an L value reference. Didn't work with just plain int or volatile int, but putting constant in there as t, that worked. What's going on here? Well, so the compiler tries to deduce t by stripping off all the ampersands, but not the CV qualifiers, off the argument type. And then if it helps make a match by reference collapsing, we'll reintroduce a single ampersand, but never two. And in this case, that actually does help make a match. You can't pass an unqualified int ref to a function expecting int ref, because that would break all sorts of things. It's nice to be able to overload on the R valueness of a thing. But you can pass const int ref to a function expecting an L value reference to a const. Why is this? And the answer, what's that? Const is const? R values are kind of like const L values, in that in C++03 we didn't really have R values. All we had was const L values. And so if you wanted to implement operator overloading, for example, you probably made an operator plus that took a const L value reference and a const L value reference and gave you back a value. And if we suddenly broke that for R values, and suddenly these things that used to basically be const L values turned into R values, and if suddenly your operator overload of operator plus or whatever didn't work anymore, well, that would suck. So very quietly, there's a little bit in the standard that says, if I have an R value and I have a function expecting a const L value, yeah, we'll just let that work. So that's why that last case works in the specific case of const. Doesn't work for non-const, doesn't work for volatile, but const is a little bit magic in the standard, and this is one way that it is. Now you know everything there is to know about template type deduction, as long as there's no variadics, and luckily that's still reserved for part 2. Only function templates do this deduction thing, right? We talked a lot about type deduction in a nutshell involved the function parameters contributing to the template parameters. So it only works for things with function parameters, and that's function templates. Does type deduction happen for class templates, alias templates, variable templates? No, it does not, because they don't have parameters. What would we deduce things from? In fact, they don't even have the special case for, well, as of 17, I think they do, but there's a special case in the syntax for functions, right, where I can say just abs of for, and I don't need to put the angle brackets. I don't need to tell it it's a template. It'll just figure that out. For classes, I do. Right? But I can make brackets empty as long as it knows what all the defaults are. All right, so let's talk about the sum expression, which gets back to your question from way earlier of what kind of thing can we put in the sub expression. Well, we need a way to specialize the template, this primary template, for a particular t. Here's how you define a template specialization. So we've got the primary template up there at the top, and that's a cookie cutter to stamp out is void of foo for any foo. But suppose we want it to be different for one of the cookies. We have one special cookie that's void. So we say template, and we put an empty pair of angle brackets, and then we write it as if we were going to use the thing, is void of void. So you stick template, angle bracket. Those angle brackets are very important. And then write the function definition as if you were using the specialization that you want to write, function or class or whatever it is. For function templates, because of their type deduction rules, this usually means you don't need to write any more angle brackets at all. But when a type can't be deduced, then you do have to write these brackets, as in that example down there. I have t, but I can't deduce it from the parameter list, so I have to put a little void in there, but if it's defaulted, I can do that, right. So here's my template specialization, which I'm specializing abs of int just because I happen to know about int min. I could do something like this, template, angle bracket. This is a specialization. And then I call it, I write it out as if I were calling it. Or in this case, template type deduction works fine. It knows that x is an int, and therefore t must be int, and it can deduce what t is. T is int. I can even write that. This is what you see most often in practice. But remember, this is just syntactic sugar for the long form. That's full specialization. Yes.
So on that, Diana said in the C++ programming language, there's no difference to having just the empty brackets and not having the template section there at all. Isn't that overloading, or what's the difference there between overloading and explicit specialization?
There's no difference between having the angle brackets after the word abs or after the word template.
To get rid of all the whole template section. So I thought that would have been overloading.
Getting rid of template, angle bracket, at that point you've just got overloading. Okay. Yeah,
so there is a difference.
Function overloading. Yes.
Okay.
Yes, this has nothing to do with function overloading because this is not a function. This is a template for making functions. Real functions will be looked for before templates. Yes. All right, that's full specialization. I'm going a little bit fast now because I have like 5 minutes left. Luckily, we have a 15-minute break coming up, so we're just going to stick around. Alias templates cannot be specialized. This is important. And the reason this is important is that in this example here, I've got a function foo that takes a myvec of tref. Now, if I were allowed to specialize myvec of t for some t, like if myvec of void turned out to be int instead of std vector of something, then I would have a real hard time with overload resolution, with figuring out which foo I'm supposed to call. But in this case, because myvec of t is always an alias for std vector of t, because it cannot possibly be specialized, the compiler can just go ahead and substitute that right in. It can say, oh, foo, and then the first argument is myvec of t, which is really std vector of t. Okay, so you've got a function that takes a vector of t, ref. And it can just remember that and forget all about the fact that it was originally declared with a template. Or, yes, with an alias template. Does that make sense? We may also come back to that later. But that's the idea of alias templates. They are actually aliases they're just synonyms that can get propagated all the way through. And so forth. It's very important that they not be able to be specialized. Class templates can be specialized. Here's the very similar example using a pre-C++ 11 way of, well, it uses the using syntax, but we have a member type def here where I have myvec of t : type, and that I can specialize if I want to. I could make a full specialization of myvec for int, let's say, and I could say using type equals double. And what that means is that when I call foo of v down here, and I say, well, v is a std vector of int, and I'm trying to match that up with this function foo that takes myvec of t : type, and like, well, I don't know what the type of mv is before I know what t is. So this parameter mv does not contribute to type deduction. So it doesn't have anything to say about t. So I don't know what t is, so I can't infer template argument t, and so I get the error. How many people have seen errors like this? Yeah. All right, well, now you know why. So class templates can't do deduction because we don't know. We'll cover that later. Now you know everything there is to know about full specialization. Partial specialization. A partial specialization is any specialization that still requires further customization by the user before it can be used. So here I can specialize my isArray type trait, which I'm making here. And I can say, well, this specialization works for anything that fits the general pattern of t bracket bracket. So arrays of some bound, unspecified bound. And then if I use it with int bracket bracket, I can say, this does match my partial specialization. TP must be int, and okay, cool, I can use that. So we have a primary template first. That uses the regular template declaration syntax. We have partial specializations where they still use template type names such and such, and they can have multiple parameters even. And then they have in the angle brackets after the name of the template, after the name isArray, they have more stuff using those template parameters. That's a new pattern that you can match when you instantiate the thing. Or you have a full specialization, which is template empty angle brackets. And again, the empty angle brackets are important. They're what tells you it's a full specialization. And then it also has something in angle brackets after there that, of course, doesn't depend on any template parameters because there are none. Notice that the number of template parameters on the partial specializations we have here are completely unrelated to the number of template parameters on the original template. The original template, primary template, had 1. Here I have a partial specialization, which also has 1, and a partial specialization with 2 template parameters. And I have a full specialization, which of course has 0. Now the TP and the N and so on, I can deduce them from whatever you pass me, but there's no way to specify them. Specialization is called. We still have like 20 slides left and 2 minutes. So for which specialization is called, first you deduce all of the template type parameters. So in this case, with a of int star, we have deduced in the primary template t is int star. That's super obvious. But then which partial specialization do we instantiate? Well, we try to match int star against, in order, well, void. Nope, int star is not void, so we don't use the full specialization. And then we look at the other two, and we say, well, int star does match TP star. TP would be int. That makes sense. And it doesn't match TP star star. Okay, so we'll use that the first partial specialization there, the third line. With int star star star, well, that would match either TP star or TP star star, right? Depending on what we call TP. But the second specialization there with the 2 stars, that's more specialized because anything of this form, I could just as well plug into this. Like the things that match this are a strict subset of the things that match this, and it's very obvious. And so the compiler will say, okay, I will use the more specialized partial specialization in the int 3 stars case. That's partial specialization. Partial specialization is allowed for class templates and variable templates because variable templates are pretty much just syntactic sugar for static data members of class templates. It is not allowed for alias templates because alias templates do not allow specialization at all. It's just no, 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 no across the board there. They're very simple, just like typedefs. But partial specialization is also not allowed for functions. Function templates cannot be partially specialized. If I have something like this, you might think that that's a partial specialization. It is not. Wrong. This creates a pair of function templates in the same overload set. It is not a primary template and a partial specialization thereof. The partial specialization syntax always contains angle brackets after the template name. Always, always, always. And in this case, it does not. And if you try to put them there, you will get a syntax error. And if you don't put them there, you will get this weird behavior where it kind of sort of seems to work until you get into a complicated case like this where I've put little snippets of code in different orders, or not in a particular order, because if you put them in different orders, you get different behavior. Here I have a primary template called isPointer, which just takes a T. And I have a full specialization, which is totally fine. Function templates can be fully specialized for void star. We also have this other thing, which looks like a partial specialization, but it's not. It's a new primary template. And if this one happened to come before this full specialization, this will be a full specialization of this template. Can you all see my mouse, by the way, when I'm waving at things? But if it doesn't, then this is a full specialization of this other primary template. And so when I call isPointer of an actual void star, we definitely deduce that, well, either T is void star or TP is void star. Well, which of these functions, which of these primary things in my overload set is a better match? Well, this one is actually a better match. Here we have a hard error here. Hard stop. Should I actually stop?
Probably. We could go on.
Alrighty. In that case, we didn't get to the end of part 1, but stick around, because there'll be more later, but right now it's a 15-minute break.